Lesson 8.4.10 on both lines, representing systems of linear equations. In this lesson, we'll use graphs to identify an ordered pair that two real-world situations have in common. We're skipping over lesson 9, so don't think that you've missed anything. And I'm assuming that you've already worked through the slides that were attached to the assignment that you might have missed. Let's take a look at some notes that might help us remember what you saw. These notes are actually replacing what you'll see on page 186. You'll need to print them out from what's offered on Schoology and insert them into your notebook to replace what's there. These notes were just way too confusing, so we doctored them up just a little bit. But the learning goal is the same. For our learning goal, we're going to use graphs to identify an ordered pair or a coordinate that two real-world situations have in common. All right. So when I talk about solutions to an equation, the solutions to an equation correspond to points on its graph. In the lesson recording, there was an equation for the graph of a tractor and a taxi, if I remember right. And here we have the equation graphed for how far a tractor is going over any given number of seconds here. So let's take a close look at what we see here. The x-axis represents seconds. And it's a little hard to see it here, but this is 1 second, this is 2 seconds, half a second, 1.5 seconds. And on the y-axis, it's measuring how many meters the tractor has gone. And here, this is 10 meters, 20 meters. So these individual lines are really going up by 2s, just so we can read this graph a little bit. So a tractor traveling 7 meters per second begins 4 meters ahead of a starting line and then travels 7 more meters every second. And the distance in meters it has traveled from the starting line after t seconds can be represented by this equation. I want to remind you of how we write equations. Starting points are like the y-intercept. That's the 4 meters. This is just good review. And the rate of change is the slope. So 7 meters per second. 7 is going to be the slope. So this line has a slope of 7. So there's our equation. And every point on this line would make this equation true. For example, if I have the point 0, 4, if I substituted in 0 for t and 4 for the distance, it would make this equation true. And every point on this line would do the same thing. So here we have the equation of a line representing the tractor. Let's find a point that will be on this graph. Well, we've already found the point 0, 4. Let's find another one. Looks like this point is on that green line. And this is the coordinate 1, 10. What's important in this lesson is to make sure we understand how to interpret this coordinate. What do these two numbers mean in this context? Well, we know that the x value represents seconds. And we know that the y value represents meters. So if we were asked what does that coordinate mean, we can say that at 1 second, that tractor has traveled 11 meters. There's the 1 from the coordinate. The tractor travels 10 meters. There's the 10 from that coordinate. So we should be able to identify what the numbers in the coordinate mean. So that's just a review of what a solution means for a line. There's an infinite number of points on this line. We could take the point 0, 4 and substitute it into this equation, and it'll make the equation true. We could take the point 1, 10, or any other point anywhere on this line, and it would be a solution. What we're looking for in the second half of Unit 4 is what happens when I have two equations. If you have two equations, you can ask whether there is an ordered pair that's a solution to both equations simultaneously. So a point that sits on this tractor line and on this taxi line. Let's take a look at this taxi line and write an equation for it, just for review. We're told here that a taxi travels at 9 meters per second and begins at the starting line. And the distance in meters it has traveled after t seconds can be represented by this equation. Well, we know it goes 9 meters per second. That's the slope or the rate of change. 9 is. And since it starts at 0, it starts at the starting line, it doesn't get any head start, I'm not going to add anything on there. That y-intercept is 0. Let's scooch up a little bit here. So we're looking to see if there's ever a time when the distance traveled by the taxi, that's the pink line, is the same as the distance traveled by the tractor, that's the green line. Is there any time, any number of seconds, where that's going to be the same for both things? If the answer is yes, then the solution corresponds to a point appearing on both lines. So we see these two lines representing the tractor in green and the taxi in pink. And what is the one point that appears on both lines? Well, it's where they intersect. And if we read our graph carefully, that's at 2 seconds, and looks like this is going up by 2s, 10, 12, 14, 16, 18 meters. So that's the coordinate that appears on both the pink and the green line. And the numbers in that coordinate mean that both vehicles will travel 18 meters. Remember, this value is meters. This is seconds. In 2 seconds. Whenever we interpret a solution, we have to make sure we include numbers in a complete sentence. So I've explained what the 2 represents with 2 seconds. I've explained what the 18 represents with 18 meters. And both vehicles travel 18 meters in 2 seconds. So what we're seeing here is that you can tell by looking at a graph when two linear relationships will be the same, because they'll be the same where the graphs intersect. That's what we're looking for a solution to our system. There's no homework associated with this lesson. We just wanted to make sure that you understood that when you're looking at a graph, a solution is a point on the line, and if you have two different lines, the solution to a system of two different lines is the point where they intersect.